limits and continuity. We want to discuss the limit of a function of two variables and also the limit of a function of three variables, and likewise the continuity of such. We start with the same concept that you saw in Calculus 1 when we introduced calculus to compute the limit. There the definition was based on epsilon delta, and likewise here. The only difference is that within the two space and the three space, whereby you have a function that depends on two variables or a function that depends on three variables, instead of discussing in calculus 1 a neighborhood on the line, where we had, say for example, the x-axis, and you looked at a delta neighborhood about some value a. So, and the radius here is delta. And so this part here is a plus delta. And then over here we have a minus delta. In calculus 3, instead of talking about a line with a neighborhood on an interval, we talk about a disk or a ball, a delta disk here, which is in the two space, and then in the three space we talk about a sphere being some type of ball that acts just like what happened in calculus 1, but you're in the one space here where f depends on x. Here a function z could depend on x and y, or a function could depend on x, y, and z. So if that be the case, then we talk about the same point that's centered, and then we can talk about what happens around it. So in shrinking delta, when delta goes small, this open disk, do we have containment? In some neighborhood that's getting closer and closer and closer to the desired point? Does that also force in the space? Does that force what happens in the function? Do those values approach some limit? Now, if that be the case, then we can talk about the limit. So here, formally, the definition for the limit of a function of two variables, let f be a function of two variables defined, might not necessarily be defined at x naught, y naught. You can have a jump at x naught, y naught, or a spike. You could have 1 over x or 1 over x plus y. And so you might not have the function continuous at the point x naught, y naught, but it's possible to have a limit there. And so we say that there's a real number L, and if you look at x and y about some neighborhood about x naught, y naught, we call that a delta neighborhood. And so this right here, this square root, defines a disk for us. And is it possible that when you force delta to be so small, does that imply that epsilon gets infinitesimally small, such that the distance between the function values and this L, this sought after limit, gets close and close and almost meaningless by restricting delta? So here we say there corresponds or there exists a delta positive, and here for each epsilon or for all epsilon positive. So the emphasis is on the existence of delta. Can you find a suitable delta? So again, my discussion earlier, by containing a so-called delta neighborhood about the desired point, does that also constrict the values about the limit, that is, as epsilon also gets small? Because there's going to be a connection between epsilon and delta. There has to be. Likewise, we discussed the continuity as well. A function is continuous in the 2 space, well, here in the 3 space, where x and y are said to be the independent variables, and z, or the function f, said to be the dependent variable. That a function is continuous, the same definition as before from calculus 1. A function here is continuous if the limit of the function as x and y approaches x naught, y naught is actually the function value at x naught, y naught. And so we got 2 or 3 things operating. That is, that f of x naught, y naught exists as a point itself, and then that this limit over here is defined, and then thirdly, we have equality. And that's how the old definition in calculus 1 is defined in 3 parts. Here in calculus 3, I suppose that you get so advanced, you just write everything in terms of just one statement and you're done. The function f is continuous in the open region R if it is continuous at every point in R. And so a function can be continuous at a point, and that's what we're defining here, or a function could be continuous at every point in some region, some open region R. So you could have one or the other. A very strong case if the function is continuous everywhere within that region. And then the continuity of a function in the of 3 variables. Well, here you go from a disk, in the 2 space, we talked about some disk where the radius is delta. In a function of 3 variables, you could talk about here a ball or sphere that surrounds the center, the point of investigation, and again the radius is delta as well. And in analysis, in real analysis, there's much that goes on with trying to prove that functions have a limit that exists by trying to find either in the 2 space a disk, or some delta disk, or here some ball or sphere. And the idea is to be able to find that function, the limit is said to be an accumulation point, by finding several of these balls to be able to prove density about a particular point to show that the limit exists. Here we will just talk about the preliminaries, talk about the definition of continuity of a function of 3 variables, and we can discuss that as well. Let us look at some problems. I think that's the goal here. 2 things: the limit of a function of 2 variables or 3 variables, and then secondly, the continuity of functions of 2 or 3 variables. Find the indicated limit by using the given limit. So here, nothing to prove. Later on in this chapter, I will show you how to prove that the limit exists based on a function of that depends on two variables or three variables. Here, this is very easy. We just use the given information. So this becomes the limit as xy approaches a and b. Here, this is set to be times 5 times this function f of xy divided by g of xy. We have some neat properties that would carry from calculus 1 to here, and that is that the limit of a quotient is equal to the quotient of the limits. And so this becomes 5 times the limit as x and y approaches a comma b of the function f of xy, and that's divided by the limit as x comma y approaches ab for the function g of x, y. And when you look at that, this just becomes 5 times the limit of f of x, and that's 4. So this is 5 times 4. Then that's divided by the limit of g of xy, and that limit is 3. And so what we have there is 20 over 3. So no work there, believe you me, no rigorous work. We'll look at that a little bit later. These problems in this section are straightforward. Find the limit and discuss the continuity of the function. Well, this function is continuous. It's a polynomial. It has no fraction where x divided by y or 2 divided by x or something like that, where you would have to examine the denominator to discuss the continuity. So we just use direct substitution and what I call just plugging in, and you find the limit. So this is 2 times 2 to be squared plus 1, and so we get 9. Here, this function is continuous everywhere. This limit can be plugged in because 0 as x approaches 0 and y approaches 2, so we get 0 divided by 2. That gives us 0. Now, in terms of the continuity, this function is continuous everywhere except where y is equal to 0. Again, we can plug this in. This becomes 1 all over 2 for the limit. And this function is continuous except at the origin, where if x is 0 and y is 0 at the same time, we have discontinuity. So look at this limit. This is the limit as x comma y approaches power of 4 comma 2. And here, if we plug that in, y would be equal to 2. And this is cosine of x times y. So this is 2 times power of 4, which is just pi over 2. We get cosine of power of 2 is 0, and 2 times 0 is 0, and the limit of 0 is 0. And the continuity of this particular function is that it's continuous everywhere. What about this problem? It says find the limit if it exists, and if it does not exist, explain why. Now, if you plug in here, x equals 0, y equals 0, that gives us 0 over 0. Now, you recall that this is said to be an indeterminate form. If it's indeterminate, then you can do one of three things. You can factor, you can rationalize, or you can use L'Hopital's rule. So here, no need to factor. There's nothing to factor. We can rationalize, or we can use L'Hopital's rule. I will choose rationalization. So this is the limit as x comma y approaches 0 comma 0 of x minus y all over the square root of x minus the square root of y. This is times the conjugate of our denominator, the square root of x plus the square root of y all over the square root of x plus the square root of y. We simplify this. The limit as x comma y approaches the origin. That gives us, for our numerator, we're just going to leave it the way it is and simplify the denominator. So downstairs we have the first term the first, which is x, minus the last term the last, which is y. So these guys cancel. So this gives us the limit as x comma y approaches 0 comma 0. Up top, we'll just have just one term, the square root of x plus the square root of y. Now when you plug in, x goes to 0 and y goes to 0. We get 0, but it's not something divided by 0. And so the limit there is 0. And then lastly, as we try to get close and close to the next section, that is this problem down here, 64, we talk about the definition for partial derivatives. But before that, it says discuss the continuity of this particular problem. Thought I had another problem there as well. I don't know where it is. But anyway, let's look at this one. This function is continuous for all x, y, and z values except at the origin, because at the origin x is 0, y is 0, and z is 0, and you would have 1 divided by 0. So here, this function you could say is continuous everywhere except at the origin, or you could say is discontinuous at the origin. So I just say the first one. So it's continuous everywhere except at the origin 0, 0, 0. Now for this problem, we show that the partial derivatives, and you don't know that it's the partial derivatives until you get to the next section, and then you'll say, oh, that's the definition for partial derivatives. Notice here that this is the limit for part A as delta x goes to 0. What happens to y? Y is treated as a fixed value. So y is held to be constant, and then the change of the tilde is with respect to x. X plus delta x divided by delta x. Now, so this is the partial derivative for the first part of f with respect to x. The second one is the partial derivative of f with respect to y. Because for part B, y is changing, x is treated as a fixed value. So let's look at the first part. So this is the limit as delta x goes to 0 of f of x plus delta x Oh, thank you. Comma y minus f of x y. This is all over delta x. So this is, yes, the limit as delta x goes to 0. This first part says wherever you see x, you're going to write x plus delta x, and y is y. So this is x plus delta x all to be squared plus y squared. Then it's minus the function, so this is minus x squared, a bad 2, crummy 2, just no, plus y squared. This is divided by delta x. We simplify. This is the limit as delta x goes to 0. Up top we have x squared plus 2x delta x plus delta x squared plus y squared minus x squared minus y squared all over delta x. Now you know that you're doing it right when x squared minus x squared cancels out, y squared minus y squared cancels out, and all you have left are terms that would have the deltas in them. It's the limit as delta x goes to 0. And this is 2x delta x plus delta x squared divided by delta x. Let's divide out a delta x from the top. This is delta x times here 2x plus delta x all over delta x. Delta x divided by delta x cancels out. The only way that you can cancel out with respect to division is with only way you can cancel out in division is with respect to multiplication. This is delta x times something else. I can't go in here and cancel that guy out because that's addition right there. So this is, we'll write it here, the limit as delta x goes to 0 of 2x plus delta x as delta x goes to 0. The result here is just 2x. And wouldn't that be the derivative of this guy if, with respect to x, if y is treated as a constant or coefficient? That is, taking the derivative with respect to x, treat y as a constant coefficient, the derivative of a constant would be 0, and then the derivative of x squared would be 2x. Well, very similarly, that's what happens for the next part. So the limit as delta y goes to 0, and this is f of x comma y plus delta y minus f of x y all over delta y. So this is the limit as delta y goes to 0 of here x squared plus parentheses y plus delta y to be squared minus parentheses x squared plus y squared, the function, right, divided by delta y. We simplify that. This is the limit as delta y goes to 0. Simplify the numerator. This is x squared plus y squared plus 2y delta y plus delta y squared minus x squared minus y squared all over delta y. Doesn't look good. Ugh. So this is the limit as delta y goes to 0. We factor out a delta y times parentheses 2y plus delta y all over delta y. Delta y cancels out. We have the limit as delta y goes to 0 of 2y plus delta y. As delta y goes to 0, the result here is 2y. Thank you.